Let's look at this slide. Hey everyone. Imagine trying to build a house of cards in a hurricane. That's what normal quantum computing feels like. But today, we're talking about topological quantum computing, a crazy approach that weaves spacetime itself to build an ultimate, error-proof quantum computer. Let's dive in. So, what's the big problem? Traditional qubits are incredibly fragile. A tiny bit of heat or a stray magnetic field can instantly destroy their quantum state. To fix this, scientists use error correction, but that requires millions of extra qubits. It's a massive headache. We need a qubit that is physically immune to noise. Enter topology. In mathematics, a coffee mug and a donut are considered the exact same shape because they both have exactly one hole. You can squish or stretch them locally, but the number of holes won't change unless you tear the whole thing. What if we stored quantum information in the global shape of the system, rather than in local, fragile particles? That's the secret. To do this, we need special particles called anyons. In our normal 3D world, particles are either bosons or fermions. But if you restrict physics to a flat, 2D plane, you can get anyons. The craziest ones are non-abelian anyons. If you swap their positions, the entire quantum state of the system changes permanently. They literally remember their history. It's mind-blowing. As these anyons move around over time, they trace out paths in spacetime called world lines. If you swap two anyons around each other, their world lines literally braid together, like weaving a rope. The quantum information is encoded in the knots of this braid. And you can't untie a knot just by wiggling the string slightly. This is why it's the ultimate fault tolerance. Local noise in the environment is just like gently wiggling the strings of the braid. Wiggling doesn't change the topology of the knot. The information is stored globally across the braid, so a local disturbance does absolutely nothing. We get hardware-level error correction for free. So how do we actually run code? Different patterns of braiding correspond to different quantum logic gates. To execute a quantum algorithm, we literally just move the anyons in a specific dance, swapping them in a precise sequence. Computation becomes pure geometry. It's incredibly elegant. Now, the catch. These particles don't just exist in nature. We have to engineer them. Scientists are trying to create them using something called Majorana zero modes, which appear at the edges of special superconducting nanowires. Microsoft's quantum division, Station Q, has bet their entire quantum strategy on making this work. It's high risk, but insanely high reward. To wrap up, first, topological quantum computing uses global shapes to protect data from local noise. Second, it relies on exotic 2D particles called anyons that remember being swapped. And third, we perform calculations by literally braiding their paths through spacetime.